want to give you a few notes that may or may not be useful to you about computing the runtime performance of the searches. In the previous video I posted, I talked about computing the runtime performance sorting algorithms. So let's do the same consideration for linear searches, for searches. So the first kind of search that you may have heard about is called the linear search. And what the linear search is all about is, in a linear search, you find a number in a sequence, find a number in a sequence of values, a sequence of values occurring in arbitrary order. Okay, so to accomplish this, we look through all of the elements until we have found a match. Okay. If an element B, say, is present in the array, size n, then the average search visited what? N over 2 elements. If B is not present, then all n elements must be inspected. Must have been inspected. Okay. Okay. So this is now the linear search algorithm works, and its runtime is BigO. Okay, so now consider the binary search algorithm. All right. Okay. You search for an item in the data sequence. So the search for an item in a data sequence that is being sorted. A binary search locates a value in a sorted array by determining whether the value occurs in the first or in the second cat. The method repeats the search in one of the halves. Okay, so number of visits required to carry out a binary search. Let's analyze that. So analyze number of element visits required to carry out the binary search. So next page. So, look at the middle elements. Right? So that's one visit. This is one visit. Then search either the left or right subarray. All right. So for instance, here's our array. We have size n. All right. So we sort it, and then we make a determination that the element we seek is, say, this particular subarray. Right. So let's take this particular subarray. Right? And since it's, and then we search for the elements in this array. So we look at the middle elements of this array. Okay? And we split the array, the two subarrays, based on the middle part. And we determine that, say, the element that we seek is in this portion of the subarray. Right? And then so we split this off. Okay. And then we determine the middle element of this array, this subarray. Okay. And then we make a determination that the element we seek is, say, here. Okay. And we just keep repeating and repeating until finally we're left with one element. Okay. So what is the anticipated order of the execution time of this algorithm? So let's calculate the BigO for this particular algorithm. All right, so for an n-element array, okay, the execution time, the order of the execution time would be the order of the execution time of half the array plus the initial examination of the middle element. Okay, so now we need a formula for Tn over 2. So Tn over 2, of course, is just equal to Tn over 4 plus 1. And then, as usual, we just substitute that back into the equation for Tn. So therefore, Tn is equal to Tn over 4 plus 2. And we just keep repeating this process until finally we have Tn is equal to Tn to the 2k power plus k. It's a k, so it doesn't look like a k. Okay. Where k is equal to the number of subarrays. Number of splits, I guess you could say, in the previous illustration. So I'll put the word splits in quote. Number of array splits. Where you're basically splitting the array into two equal halves. All right, so again, let's presume that the number of elements in the array is capped by the next highest power of 2, like we did with the sorting operators. So assume, for estimation purposes, that n is equal to 2 to some power. So for instance, suppose n is 58. Suppose you determine that n is 58. All right. Well, for runtime estimation purposes, go ahead and let n equal to the nearest power of 2, the nearest height on the high side of this, the next power of 2 past 58, and that would be 64, which is equal to 2 to the 6th power. Okay, so we can do something like that. So, using this formula, solving for k of course is equal to log base 2 then, which is log base 2 then. And so therefore Tn, or binary search, is equal to 1 plus log base 2 of n. And so we know log base 2 of n is approximately 3.32 log n. Okay. So a binary search algorithm is a log n, which is better than a linear search. Okay. Or is it? Okay. I would say yes. So let's see here. Well, let's consider. Go to the next page. Consider an array of size. Okay. So n equals 100. So what is the estimate of the runtime for a binary search? So, well, after each search, excuse me, after each search, the size of the search range is cut in half. to what? Okay, so you take your 100 element array, you cut it in half into 2 subarrays, each of 50 elements. Then you make a determination of which of those sub-elements you should search in. You cut that in half down to 25. Okay, and then 25 is cut in half to 12. Okay, and then that in turn is cut into 6. And that is in turn cut into 3. Okay. And then finally 3 is, and then 3 is cut in half to 1. And then you stumble upon the element that you're searching for. So, so after what? 1, 2, 3, 4. So how many comparisons do we have to make? We need 1, 2, 3, 4, 5, 6 here, and then of course the first comparison, which is 7. So we needed 7 comparisons. To find the elements. All right. Okay, so what is O log n? Well, so big O log 100. Okay, we determined that that was what? Found by taking log base 2 of 100. And log base 2 of 100 is approximately 6.6, which equals to 7. Okay, so they match. And note that 2 to the 7 is equal to 128. So basically, that would be the least upper bounds number of searches, the number of visits for a binary search of 100 elements. So it would be this log base 2 thing. All right.